Okay, yeah. So I'm a third-year PhD student in France, and I'm working under the supervision of Professor Magneto and Professor Grenda. And I'm here in Japan for 2 months under the supervision of Professor Katsuya Inori, thanks to the GSPS program. So this short talk is a complement to my poster. So for those who are interested in more details on chemistry synthesis and magnetic properties, so please come during the second poster session at Hiroshima University. So before starting, I need to contextualize my PhD subject, and I will introduce the research field of my supervisor. So Professor Magneto is working on molecular magnetic materials and mainly based on natural nitroxide radicals. And for Professor Grenda, she mainly works on HBN, which is an inorganic homologue of graphite, and they are well used as refractories and electrical insulator. And both are working on the same team. And Dominique wanted to combine these two research areas for this PhD subjects based on the functionalization of Borazine by natural radicals. So Borazine are inorganic compounds made of boron and nitrogen atoms, and they are well known as the inorganic benzene because they are sharing the same structure. But despite such similarities, it's well known that Borazine is less aromatic than benzene, with a charge density which is mainly located on nitrogen atom, and this is due to the polarization of the BN bond. Due to that, the Borazine is very sensitive to moisture, and water attacks the Borazine to give boronic acid and ammonia, and that's why it's very important to work under inert conditions. So one way to prevent this nucleophilic attack is to put steric inverse around the BN core. And oops. So this PhD subject is based on a theoretical study, which says that even if Borazine is less aromatic than benzene, we have a better coupling exchange between radicals. And I put here an example with immunonitroxide with ferromagnetic interaction. And as you can see here, in the case of functionalization in Borazine, we have a better coupling exchange than benzene. So based on this theoretical study, we designed a molecule which was supposed to be stable in air. And we have two aims. First of all, we have to know that Borazine functionalized by radical has never been reported in the literature. And secondly, we wanted to study the effect of the BN core on the delocalization of the unpaired electron carried by segments. So after 8-step synthesis that I will not describe here, we isolated the desired molecule. And we had single crystals suitable for X-ray diffraction. And we found that depending on the solvent of localization, we have two phases, one called alpha phase and one called beta phase. And as you can see here, even if the root space is the same with a very low symmetry, the crystallographic parameter is different. And if we check the packing, even again, if the two phases are organized into 2D sheets, the supramolecular organization is different, where here the sheets are for the 120 milliarcon, here 400 milliarcon. And the distance between the two sheets are also very different, with here 11 angstrom, here 5 angstrom. Now, if you see through these two sheets, as you can see here, for the alpha phase, the natural radicals are organized into pairs, and here for the beta phase, natural radicals are organized into triangular systems. And of course, this difference on the crystallographic structure provoke very big difference on the magnetic property. So first, in the case of the alpha phase, you can see here the value of the magnetic susceptibility is close to the value of 3 unpaired electrons, which means that, unfortunately, the natural oxide particles are unpaired. There is no delocalization through the binary. If we fit the experimental values, here is the best model of the fit. You can see here that we have a strong antiferromantic interaction with this grouping value between two natural oxide moieties of two neighboring molecules. And if we check the crystallographic structure, yes, of course, here we have a very close contact, which explains the strong antiferromantic coupling. Now, regarding the beta phase, as you can see here, at room temperature, the value is way bigger than here. And it's close to a theoretical value for spin we have, which means that we have a persistent quarter state even at room temperature. And again, the best fit, describe a triangular system between 3 Borazine molecules with a 3 half states. And here, we have an antiferromantic interaction with this grouping element. Now, again, if we take the structure, yes, as I said before, we have a triangular system. But for those who are familiar to natural oxide radicals, you know that thanks to the structure, we can rationalize the magnetic exchange, thanks to the Malkonal first mechanism. As you can see here, we have a thin packing, which provoke antiferromantic interaction. Here, we have 2 anti-packing, but the 2 natural oxide particles are coplanar, but arrange at the opposite position, which means that we have antiferromantic interaction. So we have a very good correlation between the magnetic field, the fit and the structure. So now I will show you very fresh results from neutron diffraction. Neutron diffraction is a wonderful tool and a unique tool to visualize experimentally the spin density at the molecular scale. So the experiment has been performed at 2K and 9 Tesla to reach saturation. On a big single crystal that you can see here are the dimensions. So maybe this dimension seems small, but for those who are familiar with X-ray diffraction, this is the common dimension. And for those who are doing chemistry and crystallography, you know that it's very difficult to reach this crystal for pure organic compound. So here are the results. So it's a modelization by maximum entropy. So at first we are very disappointed because, as you can see here, the spin density is mainly located on the natural oxide radicals. And I have to add that this spin density has been done for the beta phase, not the alpha phase. And we don't have indication of delocalization on the binary. Now, if you see the triangular system, so yes, we have spin density on oxygen atoms and on nitrogen atoms. And in both cases, the spin density is near the same, and it's normal for natural oxide radicals because it's well known that the unpaired electron is shared between the p antibonding orbital between nitrogen and oxygen. But again, no proof of interaction between the natural oxide moieties. But we found something very strange. As you can see here, finally, we have interaction between 2D sheets and not between all 2D sheets. Here, there is nothing. The 2 natural sides are isolated. Here, we have interaction. Again, here, nothing. So we wanted to check with the crystallographic structure. So here is the triangular system that I showed you before. And as you can see, finally, the distance between 2 natural oxide moieties between the two 2D sheets are closer than the one of the triangular system, which explains why we see more coupling exchange between the 2D sheets. And for this part, as you can see here, the two lateral side moieties are far apart with a value of 7 angstrom, which explains why they are isolated. Now, if you zoom on this part, so we can clearly see here magnetic exchange. And regarding the value of the plane between the natural side moieties, always thanks to the first mechanism of Magneto, we can see that it's close to 110 degrees, which means that we have we have ferromagnetic coupling between 2D sheets. So now we are working with my supervisor to do regarding the crystallographic structure and the charge density map to update the fitting model. And if I have one taking home message, is that this study highlights again that the complexity of molecular objects, which are very sensitive to external modification, and this external modification directly impacts the stretching and therefore the magnetic properties. So thank you for your attention.
Thank you for the nice talk. Now it's open for questions.